We're gonna go ahead and get started. There's not a whole lot of people in lecture, but at this point I gotta go because otherwise we're liable not to make it through all the way. Welcome to lecture 14. We're talking about structures and signatures, which is one part of a three-parter about modules. We're gonna be learning about modules in 3 stages. Today, structures and signatures. Next week, functors, and then next week again, red-black trees. Okay, modules is not like the hardest topic. It's difficult sometimes to get the point, but most of the things we're going to, the third lecture is not really about modules, to be honest. It's a case study. I have to say, when I was taking this course, modules was probably my least favorite topic in the course, just because I didn't really see the point. But the thing that you have to realize about modules is it's hard for me to motivate here, because what we're talking about today is software composition. We're talking about making software, writing software, because there's 2 aspects to a problem. There's the actual computation aspect, there's writing the functions, and then there's 2, the human-oriented aspect, the organizing your software. Today, that's what we're talking about. So if any of you are interested in being software engineers, this is really, really important for you, okay? And then the next thing I wanted to say was, oh, that was pretty much it. Yes, okay, cool. But otherwise, we will get started. So we have 5 things to talk about today. We're going to be talking about this idea of structures or modules and namespaces. We'll get into interfaces, also known as signatures, a brief addendum on abstraction and information hiding, and then we'll talk about kind of a result to come out of this thing called representation independence, which is a really powerful way to think about your software. Okay, and I realize that we're looking at this in ML, we're looking at it in SML, but these ideas are extremely generalizable. SML has probably one of the most sophisticated module systems out of any programming language in the world. Every other programming language wishes they had this module system, and I'm so serious about this. So let's go ahead and get into it, shall we? Okay. So far we've looked at a fair amount of language features in SML. We've seen functions, we've seen data types, we've seen exceptions, which are all the bread and butter things you need to make a programming language. And these help us solve type A problems, I'll say. Type A meaning write the function, okay? But if you only solve type A problems, no one's going to want to work with you because you're like a hermit writing code by yourself in your cabin and no one can read it, okay? Like who's the guy who wrote Temple OS? You know Temple OS? This is like a guy who thought he had a vision from God to write an operating system. So he locks himself in and writes this operating system by himself for like decades. And it was actually really cool. But anyways, the point is that guy was crazy. Don't be him, all right? Working with others is part of the name of the game, okay? So code is not meant to be just written, it's meant to be read. It's meant to be used, it's meant to be documented, okay? So what we're talking about today is how we can make that process of collaborating with others in software part of the language. And not how we can do it, but how it is part of the language in standard ML. Okay, so one particular thing that is a powerful idea for this is something called a namespace. Has anyone heard this before? This idea of a namespace. It's kind of a general sort of programming thing, right? So one example of namespaces we've seen is in the structures you've been using. I'm sure that many of you have used the list library, right, in SML. I'm sure many of you have also used, well, I'm not sure if many of you have. Maybe the list one is pretty much the only one you've used. But I'm going to tell you that there's another one called option. Or actually, no, string. String's another one. And these are modules, which I'll define for you in a second, but they're also namespaces. What does that mean? It means that for list, there is a list.compare, right? Wait, yes, there's a list.compare. And then also there's a string.compare, right? I'm sure that many of you have run into this one. But the great thing about string.compare is that even though both of these are named compare, they don't get in the way of each other. Because if I wanted to access it, I would say list.compare. And I would say string.compare. And because they live in different modules, because they live in different namespaces, these are entirely different and they don't overwrite each other. They don't badly interact. So this idea of namespaces is if I have related code, if I have code that does different things, I should organize it in different ways in different namespaces. So these are the namespaces in question, and modules allow us to do that. So that's what a namespace is. For instance, there's also like list.length. And string.size, I guess. But there's a bunch of different functions that like come underneath each of these namespaces because it's a common grouping of functions that of interest for the domain in question, which is lists or strings. It exhibits separation of concerns. When I'm programming, I want to separate my concerns. Okay? Okay, and actually, let me show you real fast an example because we can actually look at this within the SML interpreter ourselves. Suppose I said this. This is everything that exists within the list module. All of these functions right here. And so we can use any one of them. You've probably seen a few in the documentation on the SMLNJ website. I can similarly open string, and now I can see everything that's inside of the string library. But the point is that when I have a bunch of these functions, it's not really good for me to just put it at the top level and then have is substring exist and also rev exist, because guess what? For string.rev, there's also list.rev. So it doesn't do for me to have both at the top level at the same time. So if I put them into a module, now I separate my concerns and I separate my problems. Okay. So these are things called modules, and I'm going to show you an example really fast. Will I write it on the board? I think I will. So here's an example of a module. So I say module. I really mean structure. They're kind of called interchangeably in SML. So the keyword for declaring something like that is called literally structure. And we say this, okay? It's worth noting this is entirely new syntax. This is one of the few times I will be teaching you something brand new that I've been trying to hide from you for the past several weeks. So we can say, for instance, I'm going to say data type T equals bar of int. I can put a data type declaration inside of my structure. What's something else I can do? I could say val x equals bar of 5, which should be of type T, right? And then I might also say exception E of T. And then I finish it off with an end. And this is a valid example of a structure in SML. This one's a little weird, like there's no real reason for us to define this as such, but you can throw whatever declarations you like in here. Anything that can appear normally at the top level of an SML file that you've seen thus far in this semester can go inside of this structure. So this is a nice way of separating our concerns. Why? Because foo is not just a structure, it is not just a drawing on the board, it is also a namespace, meaning that if I wanted to access the stuff inside of this module, I would do something like this. In fact, wouldn't it be nice if Brandon had handily written out this thing? It's actually bar 5. Here's what we can do. All right, I can say val x, actually, I'll do it in the interpreter. This will be a coding heavy lecture. Okay, so you can see I have my module foo, but I can say val y equals foo.x. And now I have bound this thing by using foo as a prefix, by using foo to open the namespace and then access the x thing inside. And we see it's of type foo.t, not of type t, because the type t is inside of the structure foo. And then what if I wanted to raise this exception though, that we see over there? Well, I could just do that. I could raise y. Oh wait, no, I cannot raise y. Sorry. I want to raise foo.e of y. That was it. Right? Because remember, y is of type foo.t, which is the input to this exception. So I can't raise the exception without doing also foo.e. So really the thing you should remember is that to access anything inside this module, I have to prefix it with foo, because otherwise how am I supposed to get it? All right. So this illustrates a namespace that we're kind of defining and putting stuff inside of. And so everything inside there is local to that structure is one thing to remember it as. Okay. So that is a module. But we're going to see a little bit more motivating use cases of modules, because this is not quite super useful for us yet. Okay. So I've already done this. So if I had a bunch of definitions, basically, I might want to put them in different modules, because if I put them all in the same file, well, now they're all going to live at the top level. Now I'm going to get confused. Now my software is not nicely organized. So do a little spring cleaning on your code. Put it in modules. Okay, that's the idea. Domain-specific logic should live in different domains. And a side note that, yes. What type is the structure? It does not have a type. Structures are outside of the language of values and types. Structures live outside of them. Yes. Yes. Yes, you can. Question. Okay. One other note, which is that you might be like, okay, if I want to package together a bunch of values, why don't I just use a tuple or something? And yeah, you could, and the type would be gross because you'd have like a million asterisks. But the fact that structures can hold types is actually a really, really powerful aspect of it, which means that structures are strictly more powerful than tuples because you can put types inside of them. And we're going to see next lecture with functors that this actually is really, really useful. Okay, but this is, I'm showing you something more powerful is basically the idea. Let's see. And then I wanted to also tell you kind of like, how is this different from just putting stuff in different files? Because I could put everything in the foo module in file foo.sml and everything else in a different file, right? But the difference is that if I load in two files that have val x equals 2 in one and val y equals 3 in another, right? Every one of those definitions at the top level is going to go into my top level, right? Which means that now x is going to exist and y is going to exist. And this is something that we call namespace clutter. When we clutter our namespace, now x and y exist. I don't necessarily want to see everything. I want to keep my namespace nice and small because otherwise when I'm programming, I'm going to get confused at all the things that are lying around. So putting stuff in modules kind of helps encapsulate some of the stuff so you don't have to think about it. Okay. Right. Okay. And then also I wanted to kind of go to this other example here. So remember the msort function that we defined a little while ago. So if I have msort.sml, oops, what did I call it? Oh, what? Okay. Well, I thought I had it, but oh no, no, that's not that one. Okay. We're going to do this. I thought I prepared it, but I did not. Basically, what we're going to do is we're going to look at this, and then I'm going to. Great. Okay. Now don't look at it anymore. Okay, cool. So this is our implementation of merge sort, right? That we saw in a previous lecture. At least now it is. But the real thing that I wanted to tell you here is kind of like, if I have this all existing as one file, what happens if I go and I open it up in the SML&J interpreter? So if I do SML msort.sml, I'm going to get three things. I'm going to get split, merge, and msort. But if you think about it, I shouldn't have to do that because split and merge are strictly helper functions that I use to define msort. I don't really care about having access to split and merge once I'm done with msort. Msort is the only thing I care about within the file msort.sml. So you can imagine, like, if I had all of this stuff in a bunch of other files available, and we're going to simulate it by me writing msort.sml a bunch of times. Okay, if I did this, for instance, and I loaded msort in like 8 times, boom. Look at all these things I'm getting. If these had been different files, then I would be super spammed with a bunch of definitions that I don't want to see when really all I care about is this one. So let's try to figure out how we can kind of display this nicer and also make it less burdensome on the person that's programming. And let me make sure that So, okay, this was the thing I wanted to say about namespace clutter. So here's what we can do. One thing that we can do is this. There's something called a local declaration in SML. We say local, I indent all these guys. It's basically a let and end, but for declarations. So I made 3 changes there basically. I put local, I put in, and I put end, right? So like I put that local up there, I put these declarations, and these are local to this declaration. And what that means is that, like a let and end, these definitions do not escape the scope of this entire block, this entire declaration. Meaning that now, if I load msort.sml, I'm only going to get msort. Okay, this is not super important to memorize. I just wanted to show you that it's something we can do. But I'm going to go ahead and play the gross card and tell you I don't really want to do that. Why? Because I had to change my source to do that. When I'm upkeeping my documentation, when I'm trying to make my code nicer to read, I've done nicer to think about. I've inadvertently made it not nice to read. I'd like to be able to document and think about my code in a way where I do not sacrifice legibility or maintainability. Okay, I don't want to have to think, oh, okay, these are available here, and then, oh man, but there's only so many locals. Like, I don't want to think about that at all. So let's try to do things slightly differently. Okay. And so I'll show you that. Okay. So here's what we could do. For instance, I could write at the top of the file. This file contains. Oh, here's another thing I want to say, which is if I very quickly look at this file, it's not clear what's inside that I should be looking for, right? When you look at this, right, you see a bunch of code, and then you parse it a little bit and you see the local, so you're like, oh, I only care about this. But just looking at this function, now I have to read it. Now I have to figure out what it's doing. When at the end of the day, all that matters is that it gives me msort. So what I might do is I might write this file contains msort of type intlist to intlist. And then I might write down here, ignore all this implementation. And this is how C programmers do things, okay? By the way, that's not good. So I don't want to have to do this because now I have to maintain this documentation. Documentation, it's a comment. It's a comment in my source. I want to treat my documentation in a more first-class way than this. I want to be able to have maybe my language clued into the fact that I only want to expose certain things. And so that's how we're going to do things. So I'll give you another difficulty of this. All right. What if I go and I want, and let's take everything out of the local for now. Okay. What if, furthermore, I want to refactor this code? Because this is msort, which only sorts int lists. So if I want to do a little Vim magic, I would say, and then I would do that again. And then almost boom. And now it's all the CMP version, right? Now I've correctly refactored my code so that it has CMP everywhere I want it to. There's an int document. Now I've refactored it so I put my CMP function where I want to, except for the fact that now this comment is out of date. That comment is wrong. And if I am writing code and it's a Thursday night and I want to get home to my kids and my wife is mad at me and I slept on the couch last night, like I want to make her happy and I want to make sure that I write my code fast and get home to my kids. So I don't update this comment. But the problem is now my code's wrong. And are we in the business of producing wrong code? No, we're in the business of producing correct code. So let's try to do better than this. So here's how we're going to do that, right? Here's how we're going to do blah, 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 blah. Here's the idea. What if our comments were checked by the compiler? What if we had an interface that the language was clued into such that if I made a mistake, I automatically knew at trying to compile? What if my documentation was a part of the code I was writing? Okay, and that's the idea. That's the idea of a signature. And the two things we want to have in it are to tell someone, hey, I have certain declarations in this file I want you to see. And then two, the types of the things inside of the file. Why? Because remember, types are the language of love. Types are the language of code. So if I want to tell someone what my code does, I want to tell them I have msort, but in particular, I have msort of type alpha star alpha to order, blah, 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 blah. So the two things that we really want to have here are in our signature are these things. Okay, and we're going to have it be part of our language because of this stuff that we call signatures. Okay, are there any questions thus far, by the way? Because we're getting near to the end of the first part. Okay, so let's go ahead and do it. I keep hitting that. Okay, and what we're going to do, actually, I'll write it on the board with you first. So this is called a signature. So I'm going to use the keyword signature. And I want a signature for my msort module or file again. Okay, so I'm going to write signature msort, and by convention, usually our signatures are all capitalized, but they do not need to be. Signature msort equals sig end. So note the difference, which is that for the structure example, I had structure and then I had struct, but now we have signature and sig. It's not too hard to remember, I hope. And then what do I put in here? Well, I'm not going to put a value, right? I'm not going to write fun msort da 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 da. Why? Because this is a signature. I'm trying to specify the interface to a file, not the implementation. So I'm going to write what I call a specification. It's going to look like this: val msort of type alpha star alpha to order to alpha list to alpha list. Okay. This is a specification because all I'm writing is the name of the identifier that I want to appear. So this is the thing I want to be in the file or in the module. And this is the type I want it to have. And this is going to be checked by the compiler when we eventually try to mix and mash my structure with my signature. Okay. But this is the idea of a signature. It's just this thing. The one of the great things about this is, here's another thing. Okay. So if we go back to our example of msort, oh, I was actually just there. Shoot. I don't know my key bindings. If I go back to msort, here's what I could do as well. I could put everything into a structure. I could just say structure msort equals struct, and then indent everything by 2, and then put an end here. And this will be a valid way of doing things. I could do this, and then now I'd solve my problem of having all of my stuff at the top level. But what problem have I not solved? Msort still has both split and merge inside of it, because I didn't put a local. Everything inside of a module is by default visible from the module itself if I do nothing. Okay. So what I want to be able to do is, again, I want to hide the split and merge functions because I only am concerned with msort. Because you can imagine also, I realize this is a little bit of a dumb example, but if I was writing a really, really long function, one that had like 20 helper functions, I want to make sure that only my entry point, only the part of the code where outside consumers are meant to use is visible. So this generalizes and this multiplies, okay? So let's try it out. Well, here's what I can do. It would be really nice if someone had written the msort signature out for us. And the syntax highlighting is going to be weird, don't worry about it. But this is the same signature that I put on the board. And here's what we can do. I'm going to write msort.sml, but instead of just writing structure here, I haven't clued this structure into that signature yet. So I'm going to write :msort. And this is going to get, this is what we call transparent ascription. Okay, and I'll go to the slide on it. Here we go. Blah, 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 blah. Yeah. This is what we call ascription, okay? So I just take my msort module and I write this :msort. This looks like a type annotation. You can think of it about it as analogous to a type annotation, but it's not a type annotation, okay? We are ascribing a structure to a signature. We're saying that whatever msort the structure is, it should look like this to outside consumers of the library. And now if I try to load this into the SMLNJ top level, what am I going to get? 4, no 2. Yes, okay, cool. Well, first let me, wait, did I do it? Yes, I did. So I'm going to load both into SML. So I'm going to do msort.sig and then msort.sml. And now I have the msort structure, but the only thing inside is the msort value. If I open the msort structure, I'm going to get just this value msort. No merge, no split. Oh, well, that was a syntax error, but whatever. You get the point. Okay. So by ascribing, we take away certain things that were not inside of the signature. So the real benefit of a signature we see right now is I get to limit the things available, the things that you can see inside. The view into the structure is kind of filtered by this signature. You could also think of it as, okay? And that's really cool. And the next really cool thing about it is, well, what if my 5-year-old gets a hold of my computer and then decides to change my msort implementation such that now it's 2. Msort given CMP in the empty list gives me 2. All right. This is not of type that. All right. So what can I do? Well, boom. Value type and structure does not match signature spec. If I refactor my code and I don't know about it, I don't realize that I'm no longer fulfilling this contract, the compiler knows and the compiler complains. This is a contract. I'm saying to the outside world, I'm presenting myself to the outside world in this way, and then this is what people get to see of me. Okay? What's that? I don't know. Yes. What's up? What kind of mutation are you thinking of? No, indeed. Well, change. Okay. When we get into imperative stuff in the very last lecture, we are going to see that you can change mutable fields, but if your structure contains purely immutable stuff, then yes, you cannot change anything inside. Okay. It's a tricky conversation when you get into mutability, as everything is. But yes, pretty much. I'll give a high chew for that one. You know, I haven't get enough to high chews recently. So who wants a high chew? All right. No, I'm just giving it to random people that. I'm sorry. All right. All right, that's it. Okay, fine. You still have your hand up. Fine. All right. Anyone on the side? Okay, yeah. All right. I'm literally giving them out for free, so I don't know why people aren't raising their hands. But anyways, okay. All right. That's enough. No handouts. Cool. Okay, now that I have your attention, let's talk about taxes. I'm kidding. All right, so we're checking this with the type of the signature. All right, that's the main thing you should think about. So if I wanted to write it out, I would say benefits of having signatures is 1, hiding declarations, hiding parts of the declarations that we don't care about, like helper functions and etc. And then 2, specifying types. Because if someone is using my library, I want to have a contract that I'm upholding with them. If I am providing a function that takes an int and I go and I change it to taking in strings, I want people using this library to now have their code no longer compile. Why? Because otherwise, if they give me a string, bad things are going to happen. So let's try to avoid that. Okay. Here are the benefits. All right. But let's move on from that, shall we? Okay. And as I mentioned, yes. So this is all the stuff that happens, right? This is pretty much everything I said. Okay. Maybe we'll finish early. Cool. All right. Any questions on signatures and structures? Because I'm introducing something brand new. So if you have questions, might as well. Cool. All right. Abstraction is the next thing I wanted to talk about. So if I have my M sort signature, let's take a look and talk about this. I'm gonna take a little bit of a brief detour, but I've already kind of harped on to you about abstraction, but I want you to really feel the abstraction today. I want you to feel like a carpet burn. Like this is really important for what we're talking about today, because abstraction is how we view software. And when you work on software, you can't just think about what the code is doing all the time. You have to have high level like notions of, oh, this code goes and like changes this thing, or like delivers a request to where, rather than thinking about the very nitty-gritty details of what's happening. And whenever I think about this, I'm reminded of our slogan in this course, which is functions are values. And I'm not wearing the jacket for you. But as a bit of a side note, I was at a security conference like a few months ago, and I was wearing my functions are values jacket. And then this guy like comes up to me and he looks at me and he like kind of walks around and he's like, don't you know that functions are just x86 assembly? And then I go, actually, I went to CMU, so yes, I know that. Thank you. But one of the things I think about when I think about that is that there's a particular kind of person that thinks it's a big gotcha to go, functions are pointers, or oh, computers are just bits and bytes. And it's so ludicrous, because people say, for one thing, ignorance is bliss. Well, I'll modify that a bit. I'll say that selective ignorance is a gift. If you're able to do it, then you should. Here's the point. Do I know deep down that computers run in the real world and there's real hardware that is running all of our code? Yes. But that doesn't change the way that I view my code, the way that I think about it when I want to use it efficiently. It's kind of like, you know, if someone goes up to me and I say, oh yeah, I got some of my favorite fruits, you know, I got strawberries and I got apples, and they're like, did you just say that apples are a fruit? Don't you know that apples are made of atoms? And I look at them and I'm kind of like, yeah, thanks. Anyways, and I go talk to my friends because I don't know what this person is doing. But the point is that something being something else, if you go down deep and you really take out your magnifying glass, does not change how you should think about it in your everyday life. Am I going to rock anyone's world if I tell you, hi, you're all made of atoms? Does that mean I can not treat you as human beings? In fact, no. Okay. So it doesn't matter what something really is. It doesn't matter what something is. It matters what something should be, kind of, in a sense. The other thing I also have an image of is someone going to the grocery store and being like, excuse me, manager, you have tomatoes here under the vegetable section. Don't you know that tomatoes are botanically fruits? The manager is not paid enough to deal with you, okay? This is what I think about whenever someone comes up to me. It's like, don't you know that functions are really pointers? Yes, I do. But I choose not to think of them that way. It's not a comment on my knowledge. It's a comment on how I choose to interact with the world, okay? IT 213, I know this stuff, all right? Trust me. So abstraction is what I want to really care about here. I want to be able to have higher level models of things than they really are. Because at the end of the day, that's kind of what we do in real life, right? If I want to understand anything with my little human brain, okay, I have to put it in little human terms, which are humans and functions and big, you know, like little routines that go and they anthropomorphically go and they trade information, okay, Alice and Bob. So that's why we choose to think about evaluation of expressions, not bit flipping and hardware, okay? One of these things is nicer than the other. So to bring all this around, Same thing at the software level. I want to think about only the things that are relevant to me. If it felt like kind of trivial to you that I hid merge and split, oh, how interesting. It's really important because I only want to care about the limited things that can fit in my little human brain. If anyone here thinks like you're like a 10x engineer and it's not going to matter to you, you're going to be able to wade through the garbage, I salute you and I wish you luck in life, okay? But I prefer to think about things in ways that are easy for me, okay? And I think most engineers do. So that's my diatribe to you, okay? All right, so the point of specification is ignore the parts that are not relevant to you, okay? And signatures and structures are going to get us there. All of this is to say, really, that this signature I gave you is actually kind of terrible in that regard. Why? Because I said my signature is M sort and my value is M sort. What is the one value you expect that is going to be put in the structure reasonably? Probably the function merge sort. It would be pretty weird if I like implemented a function that gave you always the empty list, for instance, okay? That's the only sensible thing. But I'm constraining my implementation here. What I mean is if I give you a function, or I give you a structure, and I tell you I'm giving you a sorting function, I should be able to leave it at that. I don't care what the sorting function is. I care that it is a sorting function. Because what am I going to do when I use the sorting function? Am I going to go and run through the M-sort algorithm in my head and like divide and conquer and then make sure that it makes sense in my head? No, because sorting is a very clear specification. So what I'm trying to say is, let's erase 2 letters. This is a better signature because this is a signature that can be ascribed to you by multiple implementations. It's a signature that's useful to me as a programmer because why? I look at it and I don't care what the sort is. I just care that it is a sort and it's fast enough and I want to sort. I don't want to write it. That's it, okay? So that's all to say this. Oh yeah, there's also a comment. Yeah, okay. Some of you are going to be like, oh, but M-sort is unlog n. Yeah, so is quicksort. So is probably other sort. I don't know. The point is that it doesn't matter as long as it runs fast enough, which you should be assured of. And we are not yet at a point where our specification can type check cost bounds. Actually, that's impossible. But that would be pretty nice. So here's our updated signature because I want to be able to remove as much irrelevant details as I can. I don't care that it's M-sort. I just want to think about my code. I don't care about your code in the library, okay? And that's a sad truth, by the way. So if I wanted to do this out in code, what did I put it in? Oh yeah, M-sort, wait, no. Oh yeah, I have an insort I defined here. I defined insertion sort for you, and you don't need to think about what it does, but first, actually, let me do this. And then let me go back to my M-sort signature, and let me blatantly lie by changing it to sort. And if I do msort.sig and then I do insort.sml, I'm going to get a type error because I messed something up. Oh, oops. Okay, the point is here, I forgot the CMP function. But if I had not forgotten the CMP function, this would have worked. In fact, do you care enough if I, okay. I don't care enough. I have time. I got time. Oh, whoops. Oh, whoops. No. I did a, this is why it's more important to have things in text replace. Okay. Does this look good to everyone? Yeah, okay. Yeah. Thank you. Thank you. There we go. All right. So okay, let's go back. So the point is that what I did is I made it so that insort actually takes in a comparison function too. As you can imagine, like if I had insort like we wrote it earlier in this course, I wrote it specifically to int.compare, but I don't need to, right? I can make it as general as my msort. And now this value sort here, I use partial application. If you want, I can write it out more explicitly. I can write fun sort CMPL is equal to insort CMPL, if that makes you feel better. This is the same type as the msort that I've defined. Whoa. This is the same type as this. Oh, yes. These two things have the same type, okay? So I should be able to do this. 140. msort CMPL. Jesus Christ. And if I do msort.sig and then msort.sig and msort.sml, this will also type check, okay? Does everyone get the idea of what I'm saying here? That I can have two different implementations of sorting. Doesn't matter if it's merge sort or insertion sort, but both are visible or both are describable by this signature right here, okay? The same signature that's on the board, okay? So it doesn't matter what my implementation is if my only view into it is this description. I abstracted it away. Yes. Sadly, no. Sadly, no. Yeah, so remember that one of the things about a valid comparison function is that it's a total order, which I defined for you as meaning that you can put it on a number line. Like I can put my values on a line, and then if they're less, according to this number line, they'll be less, and then otherwise equal, blah, blah, blah. And the question was, can we verify that this thing is truly a comparison function, like in the specification? And we cannot do that. That is a hard thing to do. In certain programming languages that are very, very wildly different than programming languages you've seen, you can. But that is at the cost of making type checking essentially the same thing as running an arbitrary program. Basically, you run a program on your type. Anyways, that's an aside, very much an aside. But yes, any other questions on structures, signatures, anything like that? Does everyone get the idea of like why it's better to have this in the M sort signature? Give me a temperature check. Thumbs up, thumbs down, thumbs sideways. Okay, cool. All right. PA stand up? Nope, not today. Not any day. All right. All right. Go take your quizzes. Get up. Blue team here. Thumbs of any kind. Cool. All right. Well, we're gonna move on. You're never gonna guess, by the way, why the password was what it was. But anyways, the next thing that comes with this. Okay, so let me rephrase that. What we saw already with structures and signatures is pretty cool. And I showed you two different forms of kind of lessening your cognitive load, which is kind of a big theme in software systems. When you're architecting any kind of project, you want to think about the best way to present it to yourself, to your collaborators, to your, let me use a tech buzzword for you, to your stakeholders, okay? But you want to think about the best way to structure your code such that it's very easy to think about. So to that end, the way that you think about things is by thinking about less things. We're going to keep with that mantra here, which is that we get power through selective ignorance by hiding more things from consumers of our code, okay? And that's the idea of what's literally called information hiding, okay? Information hiding is how we're going to make our libraries more palatable. So recall that structures can contain types. We haven't looked at any that have that yet, really, except for the one silly example I gave you. But we can have types inside of a signature, and structure. So let's consider a signature which describes a library for sets of integers. Okay, and when I say library, I mean this code will be shipped off to someone else in like Cambodia, and they will load up their SML interpreter, and then they'll get the code and then use it. Okay, I mean third-party code that you might write that somebody else in the world is going to use. Maybe it's you, again, or maybe it's someone else entirely. Okay, so we're dealing with two different problems here, and this is the signature I might write for that. Okay, and let's work through it a bit. But the signature says that we have a type T. And this intset.t type should be my type of integer sets. I haven't said what it is. I haven't told you what the type definition is, but this is fine syntactically because I'm saying that anything ascribing to this type T or to the signature intset needs to give me such a type. I don't know what it is. I don't care what it is. I care that whatever implements this knows what it is. Okay. So the idea is that the interface just has this type. And then I have four values. I have the empty set. I have a function that takes an int in a set and gives me another set by inserting. I have a function that removes an integer from a set. And I have a function that checks for membership of an integer in the set. Okay. And this should seem like a reasonable interface for sets. You know, there are a few other helper functions we could put in there, but this is pretty much all we need to get rocking. Okay. And so the real point here is that I don't really care who implements this, but the structure that ascribes to the signature needs to have these methods of this type. It has to. And granted, a valid way to fulfill this type is to like write nonsense, okay? To like write raise fail unimplemented. That's true. But this is the best guarantee I can give you, which is that at least these functions have these methods, or sorry, these functions have these types, okay? So let's take a look at that in code. So, all right, if I were to open up my set.sig here, this is my signature for sets, and it's all green because I didn't bother to set up my syntax highlighting. And then I'm going to tell you that this, in fact, is such an implementation. All right, and let's walk through it. Okay, so this int set, I haven't ascribed it yet, okay, but I will. It implements the signature that we see on the left here. How? Well, first I need to define the type T. So I say that the type T is going to be int list. We're going to represent sets using lists. It's an easy way to do it, okay? And then I've got an insertion function. When I use my insertion function on nil, I get the singleton. If I do it on x cons x's, I check if it's equal to the first thing. If so, then I don't do anything. Otherwise, I put it in, and then I recurse. Oops. Wait, no. Wait. Geez. Okay, this is just wrong. If I should check that if it's equal to the first thing, then I put it in, and then otherwise, if it's not, then I need to recurse. Oops. Wait, no. Okay, you know what? Shoot. Wait, I need to think for a second. Shoot. Okay, I'm trying to do two things, which is put it in. Okay, yeah. You know, actually, no, this is fine. I know what to do. There we go. Yeah, okay. So otherwise, I just recurse and I put it in, and then eventually I'll reach the end of the list, and then this will be put in. I was caught between wanting to do the comparison and the insertion at the same time, but they should happen in two cases. So otherwise, I just check whether or not it's the same, and then if so, I don't keep this v. Otherwise, I do put the v into the rest, and then I keep the thing on the front. Okay, and then the same thing should happen here. Actually, you see that actually by analogy, it's exactly the same thing. Where I'm going to say that if v equals x here in the remove case, I take off the x. Otherwise, I keep the x and I remove v from the rest. Okay, and that should be fair enough. And then for membership, if it's the empty list, it's false. And then if I want to check membership of v inside of x cons x's, it's either the first thing or it's a member of the rest. Okay, is this fairly clear as like a simple implementation of a set library? Do people think it works? Okay, that was not a gotcha. This one does work. It could have been a gotcha, but well, it was a gotcha for me. Anyways, so this implements the int set signature in a nice way. In fact, what we can do is we can then say, let me ascribe it to int set. All right. So let me try to do that. If I do this, I'm going to get these things, which don't matter, but I'm going to get that indeed int set as a structure ascribes to int set the signature. So if I open, and I didn't really mention this before, but you know, open lets you take everything in a structure and then dump it out into the top level. I get all this stuff. Okay, but the real important thing to see here is this. The type of intset.t is int list. Now, that should make sense to you. I said that to you literally like 20 seconds ago. But if somebody's using this library, if I'm this programmer in Cambodia, okay, I should not be privy to the details of how the library is implemented. Why? Because here's what I'm going to do. 1, 2, 3 is of type intset.t. Oh, sorry, that's fine. 1, 1, 1 is of type intset.t. A valid set is the list 1, 1, 1. Let's take that to its logical conclusion, shall we? And so this is the oh yeah, that's also wrong. I'll fix it later. So anyways, something else I should also say is like this kind of ascription that I do here with the colon is called transparent ascription. And you should think about it, that should, as a hint, that I'm going to tell you about a different kind of ascription real soon. Opaque ascription. So here's my code for you. All right. I say that a set of type intset.t is equal to 1, 1, 1, 1 in a list a bunch of times. And then I tell you, hey, this is a set without 1, I promise. And it's by removing 1 from the set. And then I run this code. If 1 is a member of set without 1, I promise, then I destroy the universe. Otherwise, I don't. Okay. This code destroys the universe. Okay. All because you couldn't keep your invariants in line. You couldn't keep your ducks in a row. If I'm the consumer of this library and I can just go in and meddle with the internals of the implementation however I like, I'm perfectly free to do stuff like say that this is a valid intset.t. It's a valid list, but if you think about like our invariants that we have here, you cannot produce this value from any sequence, or rather, does anyone think you can produce this value from any sequence of operations that were in the int set library? You cannot, because I will always, maintain that there's exactly one of every element inside of the int list. Okay, so this is a int list to the compiler, but really it's not. So let's do better. The idea behind opaque ascription is I shouldn't be able to ever see what this type is. I don't care. All right. So if we do this, here's what we're going to do. Boop. This is called opaque ascription. Opaque ascription is just where you put a greater than symbol after the colon. And what it means now is that if I write SML set.sml, I get the same thing, but now if I open int set, type T is unknown. I have no idea what type T is. And that means that if I try the same trick, I get a type error. The compiler is going to tell me, hey, what is this nonsense? You're saying that a list, int list is of type intset.t? No, it's not. And it's kind of an interesting thing where it's sort of like a parent keeping you inside the little playpen, and they're like, no, you know, like Santa's real, Santa's real. Great, I'm gonna spoilers for you. Santa's not real. Okay. Same way that this list is not an int set. All right. The compiler knows very well that this list is in fact of type int set. But to you, the consumer, the person writing the code, you shouldn't know. So it doesn't let you do it. Okay. I'm going to show you an example of how we program with such an interface. So first, let me clean up. I don't need to open it. Okay. So what this means is now, if this is what I call an abstract type, and that is a vocab word, by the way, so I will write it down on the board. The type T is called an abstract type, which is also the name of Robert Harper's blog. But actually, it's existential type, sorry. But an abstract type is a type that I have no idea what it is. All right. It is implemented by somebody, but then they took away my toys by using opaque ascription. All right. So I have no idea. And this means that the only way to get a value of type intset.t, how can I do it? The only way is through this library. I'm only permitted to interface with sets through this library. Okay. And that means I can do stuff like this. So let's say that val s is equal to intset.empty. And then val s, and here's what it's going to do. SMLnj will print out to you a hyphen. Why? Because it can't use the printer for ints, or int lists. You don't know that it's an int list. Okay. So it's very hard to see when it's inside. Okay. You usually have to write a separate helper function to like show it. But let's do another thing. Let's do val s is equal to inset.insert. Let's do 3 into the list or into the set. Oh my god, I should have done RL wrap. Okay. And then let's insert 2 into s. And now if I do inset.mem2 of s, I'm going to get true. If I do inset.mem1 of s, I'm going to get false. And if I do inset.mem3 of s, I'm going to also get true. Okay. It behaves like a set. And you should be assured of that because we just implemented it and you were assured that it was correct. So this means like put yourself in the position of the programmer in Cambodia who doesn't know how it's implemented. This means that now this is all I see. I don't get to meddle with things. And also, I don't have to think about how it's implemented. I don't know how it's implemented. So even though we implemented this literally like 5 minutes ago together, I'm going to do a little Men in Black. Don't worry about it. Memory wipe. Okay, is that a dated pop culture reference? The point is that you forget how it's implemented. Because when you're working on code, even to yourself, you shouldn't have to remember literally everything that's going on in your code base. You should be able to think at the high level. Okay. So let's go back to the slides real fast. So in particular, what this lets us do is we can maintain invariants. If nobody can interact with my library except for my functions, I make sure that my invariants are always respected. Namely, the set invariant, which is that I should only have at maximum 1 of each distinct integer in my set. Okay. All right. So anyways, I showed you this opaque ascription stuff already. Okay. All right. And this means that now we can never destroy the universe, by the way. We can never destroy the universe with the code that I had previously, because any value of intset.t truly should never have that 1 is a member of it if you literally just removed 1 from it. Okay. And this is just a bunch of code that I already did with you. Blah, 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 blah. Okay. Here's the thing I wanted to say, I think. One comment I kind of wanted to have here is like, as a programmer, you are producing code for yourself and others. I've said this a lot of times, but this really shines through here where I'm going to tell you, like with opaque ascription, you have no idea what the int set is, even though the part of your brain, the half of your brain that implemented it 5 minutes ago, does. But your working brain, the one that's like actually using this library, when you act as the consumer of the library, you know as little as anyone else. So it's a tenuous stance where you are both the consumer and the producer of this library, meaning that you should be able to produce a clean API that leaks no inside information, and also use that API in a way such that you can maintain your conceptual knowledge. Modules are not perfect for this. Remember, there's a lot of ways that we can satisfy the signature of int set that don't behave as a set should. But like that's not on us. That's on the program. Okay. The best we can do is give you a type. All right. Okay. So close your eyes, think like a user is the mantra for today. But here's a couple of reasons why you should care about it again. And I kind of said some of this, but again, it lightens your conceptual load because what would you rather think about? Would you rather think about the code that's like stepping through, or do you rather think about the high level set? And then 2, you can't break your own invariance. Remember, self-defense against yourself. If I write this destroy the universe code, I want to make sure that I can't break my own invariance and produce an invalid set. And you can't if you use opaque ascription. And then 3, it helps you maintain your code because if you refactor your code, for suppose like I got tired of int sets, okay, int lists for int sets. And so I went into my code base, right? I went into my code base and I literally like, blah, blah, blah. I went into set.sml and I changed this int list type to like int tree. And then I refactored all of this code, okay? Say I did that. If I did that, because of opaque ascription, as long as I maintain my invariant inside my internal representation, I don't have to change any code anywhere else in the world. Why? Because if I have an opaque type, one thing to note also about opaque types is if I have val s equals int set.empty, if I want to do case s of nil goes to 1, I can't. It doesn't type check. So I can make outside of the interface, I can make no assumptions about what's inside. So that means I can refactor my code here for free because I can never violate a type assumption if I change just what's inside. Does everyone understand what I'm saying here? Like, I don't have an example handy, but like because of this opaque ascription, if I change my internal library, it changes nothing anywhere else. Does that make sense to everyone? Thumbs up, thumbs down, thumbs sideways. Okay, all right. And that's a real advantage when working in a big code base, okay? Okay. Yes. The fact that SML modules can enforce this abstraction layer is really freaking powerful. I realize that like this stuff about like signatures and types is not necessarily super new, okay? There are other languages that can do something similar. But this idea of abstract types is really powerful because not a whole lot of languages can enforce that you can literally never break your invariance. I can never produce well-typed code such that my set has 2 entries in it that are the same, okay? All right. Any questions on that before we work in representation independence for the last 20 minutes? Y'all are savants. Either I'm motivating this well, or all of you are thinking, why do I care about this? And you're not saying it, okay? Don't be polite, all right? Feedback is a gift. All right. The last thing we're going to talk about today is something called representation independence. And this is going to show up on your homework, I'm pretty sure. There's a proof that has to do with this. I'm just going to give you the high level conceptual idea, okay? So I've said a couple times before, but this class I've trained you, I have conditioned your brains to be miniature SML interpreters. And some interpreters, you know, like I don't expect you to know everything, but so far all of you have pretty good SML interpreters in your brains, okay? But it's ultimately inefficient. I've said this a couple times this lecture. It's inefficient for me to literally run Mulligan in my head and then step, because I'm not going to be able to remember. Okay, I can't even compute the 6th factorial in my head. All right, like how am I supposed to step like the factorial implementation or the set implementation? So one thing I've tried to clue you into is using invariance instead of thinking about what your code's doing. Instead of if I wanted to do like fact of 6. Like, yes, okay, you could very well step this to 5 times fact, 6 times fact 5. And then do the whole chain of equivalences all the way down. But why, when you can say, hey, post condition, fact 5 is equal to the factorial of 5 in math. And then if I do 6 times that, obviously I should get 6 factorial. Why do the evaluation trace when you can think about your code at the level of your invariance? I'm going to do even better for you this lecture. We're not going to think about invariance. We're going to think about pictures. So the idea is this, all right? Take this code. All right, if I ran this code, I say inset.insert. I should have used pipes. I would have rather used pipes. And you should have rather that I use pipes, by the way. But I insert 1 into the set, the empty set. Then I insert 2 into that. And then I insert 3 into that. Okay, your conception is you should probably end up with the set 1, 2, 3. And in fact, because of our representation, the fact that our code is correct, we do. But which is easier to think about? And oh wait, I remember what I was going to do. Which is easier to think about? Inset insert 3, inset insert 2, int set.insert one int set.empty. Which is easier to think about? This. Oh shoot. Okay. Oh wait, I think. No, I think I pushed a patch last night, and I think I forgot to recompile. Okay. Well, anyways, the point is that actually we can do this. Here's what we can do. We can watch the one I recorded last night. So would I rather think about this, which is, by the way, like a whole smorgasbord of nonsense. Let's look at all those friggin' cases, and okay, eventually we end up with 3, 2, 1. That's true. Oh, it was because of the description. That's why I forgot about that. Would I rather think about that, or would I rather think about this? The picture in your head, which is that int set.empty. You have no idea what it is. Hey, but remember concepts? I'm going to give you a little bit of trauma. We're going back to it because that's the notation for the empty set. I insert 1, I go to the set 1. I insert 2, I get the set 1, 2. I insert 3, I get the set 1, 2, 3. Instead of thinking about the code, think about the picture. Think about what the set is at the high level. That's what representation independence is going to do for us. Independently of our representation, we can think about our code. So it doesn't matter how the structure is implemented, so long as it behaves the way I should. Some of you may have heard of the duck test. If it walks like a duck, swims like a duck, pays taxes like a duck, it's probably a duck. Okay. Same thing with your sets. If it behaves like a set, inserts like a set, removes like a set, it might as well be this picture of a set right here. Okay. So just think of the picture. All right. So I'm going to define to you representation independence is where I can use a library independent of how it's represented. And ideally, if I have any library that's exporting an abstract type, it should be representationally independent. It shouldn't matter if it's lists or trees, as long as it gets the job done. Okay. I don't care what your code's doing. I don't care what the data structure is. I care that it's implemented in a relatively efficient way, and then it's correct. Okay. But correctness comes first. All right. So for instance, let's think about the difference between these two code fragments. Okay, yeah, that's what I was also going to do. So let me just do it in here. I'm going to make it a little bit more simple, and then I'm going to do this. Let's think about the difference between these two pieces of code. And let's not opaquely ascribe. Let's make it transparent. What do you expect to see out of SML when I load this into the interpreter? Any guesses? Actually, so you shouldn't see anything because I didn't bind it to anything. What should you expect to see out of SML? I think it's actually the opposite. But yeah. Anyways, the point is that these are different values, right? Like these lists are different. I think that we're far enough in this course that we know that. So what gives? Why do I have two different values here? Which should be mathematically, if we look at like, well, it's gone. But if we look at what I just did, because they're representationally independent, like they fall into the same, now here's another math term for you, sorry, equivalence class of values under this int set library. Okay, what I mean by that is these both denote the same set. They're different values, but why do I care? Because if this were opaque, right? If this were opaque and these were hyphens, I would literally not be able to tell which one was 1, 2 and which one was 2, 1. In fact, I wouldn't even know that it's a list. It doesn't matter to me at all. So they fall into what I call representationally equivalent classes. These two values are the same modulo equivalence under this structure. Yeah. Yeah, that's why it's not in blue. Or that's why it's not colored. Yeah. I call it a representationally equivalent class. Yeah, thank you. All right, so here's the picture, right? These equivalence classes are themselves these big circles here, and I can go in between them by doing certain operations that are labeled with the edges. And the mathematical set that these are meant to represent is at the top. So the list of singleton 1 is meant to represent the singleton set of 1, and then 1, 2, or 2, 1 could represent the singleton or the set of 1, 2. Either is possible. And then same with this, right? And there's a few more, but they don't fit, all right? But all that matters is that if you are in any one of these buckets and I take one of these edges, I do an insert or a remove or whatever, I will go between the classes. I don't care what specific value I have as long as it's between these classes. And that's kind of the conceptual idea, which is that we are partitioning our values into classes of what I'll call like observable behavior, right? Does everyone understand what I mean when I say like everything in this bucket, all of these values behave the same if they were to be opaquely ascribed, like behind the curtain, behind the wizard, right? All these behave the same, right? So it doesn't matter at all. I'm just going between classes that are the same. And then I can also get out concrete things that are not just sets. I can get out false and true if I did like inset.mem2 on the singleton list of 1 or the singleton set of 1, or so on and so forth. All these examples you can read through. Okay, does this diagram make sense to everyone? And there's like infinitely many nodes and edges I'm missing. Okay, but I didn't have space for that and I didn't have time. Okay, so they're equivalence classes of observable behavior. Another thing I wanted to say is like this kind of means that you can define a relation. You can define like a mathematical relation, like relating two values, like takes them to lists and then gives out true or false. Okay, and all of these things in here are related because they must behave the same. The point I'm trying to get across here is that representation independence is good for your conceptual thinking. It's also good because you can prove that these classes exist. You can prove that we can never, ever, ever get two values like this that are behave differently. Okay. But we can generalize this idea. It's not specific to sets or in lists. What if I had represented inset with trees? Well, let's do it. Okay, so I'm going to write out the trees, and remember that trees is long and nonsense. So I'm going to abbreviate node as n and then empty as e. Okay. But the diagram looks the same, doesn't it? So if I had implemented inset with trees, I would have that this is the singleton set of 1, and then these are the possible singleton sets of 1, 2, and then the possible sets of 1, 2, 3 in this tree representation. But if I go between using the arrows, which are not labeled anymore, but they're the same as what they used to be, because I didn't have space, it's the same idea. So what I'm trying to say is think up here, not down here. And when we use our type system, when we use opaque description, people are forced to think up here. Doesn't matter what your representation is. I can go so far as to say, well, if these diagrams are the same, here's the real cool thing. The most important idea is that we can use representationally equivalent classes to prove that two different implementations are mathematically equivalent. As in, I can prove to you that if I implemented int sets with lists and I implemented int set with trees, I can prove to you that no sequence of operations can ever produce differing behavior. I don't ever get a divergence in behavior because I maintain my invariance. And if I had the code for both, I can prove it to you. And you will prove this about something. Also sets, I think, right? Yeah, also sets, probably with a different representation. So it doesn't matter whether or not the values came from the same structure. We can think of the picture as still having these equivalent classes. And here's what I'm going to use a bunch of pictures or a bunch of colors again. Boom. So I can have the picture, but up here in the green, I've got the trees, and down here in the blue, I've got the lists. And the idea is that I can relate values from this implementation, the trees, to this implementation, the lists. And I can relate them in a way that I can prove that I only ever end up in these buckets. And all observable behavior from like mem or other functions must be consistent with that. I always get the picture. Okay. And that's kind of the ultimate way of proving that like something is correct, because I can start from my inset with lists, and I can make it even more efficient or hard to understand implementation. But as long as I have my representational independence proof, as long as I prove that they go into the same buckets, then it doesn't matter. They work. It works as it should. Okay, and that's the proof that you're going to do on your homework a little bit. So formally, let me say that the relation is R that takes in S1 and S2 in green and blue, such that S1 is of type intSetList.t. Assume that I had intSetList and intSetTree as like two structures where I implemented the same signature. And then S2 is a value of intSetTree.t. And I want to prove that the relation is preserved by all operations in the signature if I start from the empty case. Okay, no matter what I do, I'm always going to preserve the signature. And so to give you an example, for instance, if I had 1, 2, and then I had node of empty. I'm going to write this out because I don't have anything else better to do with my time. 2, empty. If I write out these two values, I can show that these are related by R. Whoops. These are related by R. And I can show that no matter what I do, if I insert to both, if I do an insertion of 3 to both, or 3, and these would be different insert functions. It would be the list insert function here and the tree insert function here. I can prove that the outputs are still related, whatever the result would be. And then I can prove that no matter what happens, I always get the relation preserving. And because the relation preserving is preserved, mem is going to give the same output no matter what I do, as long as they're related. So like mem of 2 is going to give me true here. It's going to be true here. And it's also going to give me false if I do mem of 3 on both. Okay, that's the idea of the representation independence proof. Okay. If you don't think this is important to know, it will be when it shows up on your homework. I'm just trying to give you like kind of a conceptual idea of what you're going to be proving. Any questions about representation independence, which is not strictly to do with like the software part, but it has to do with how we are assured that our code is correct. No questions? Okay. I have to go here because I don't have a pointer anymore. So I want to finish off this lecture by saying, like, it might seem like this is not necessarily practical. I understand. You want to get back to the hops and the CPS. I know you love CPS, and you want to write some code. You don't want to organize your code. Organizing code is for suckers, okay? I write the cool functions. I don't have to maintain it. If you're a software engineer, by the way, that's not true, okay? You're going to remember, I spend 95% of my day at my desk thinking. I spend 5% of it coding, okay? This is an extremely essential part, and it has a lot of practical applications, even though in other languages, they don't have modules, because they have stuff that's similar, and they have interfaces. This idea of interface and implementation is global. No matter what language you go to, no matter what software you're working with, it's going to be a thing. And then abstract types are really cool. Like this idea of having representation independence and opaque types that you have no idea what they are is really powerful because it stops you from ever breaking your own invariants. In 2 lectures, we're going to see a really powerful use case where we can write an abstract type of self-balancing binary trees that we can never, ever, ever mess up. And it is impossible to produce the value of that self-balancing binary tree that is not balanced and not a BST. Okay, it's going to be called red-black trees. All right. So again, self-defense against yourself. Maintain your invariance for yourself so you can maintain your invariance for people using your code, for your manager, okay, in like 3 years. All right, that's all you need. We finished early. Thank you so much.